This is practice test 2 for PHYS1231. So in this question, we've got a capacitor with a charge of So in this question, we've got a capacitor with a capacitance of 4 microfarads, which is attached to a battery like this. And the battery has a voltage of 12 volts. It's then disattached from the battery and connected across a second capacitor. So now we've got the situation like this, where we've got C1 here and C2 here. And then we're asked what charge is stored on each of the C1's plates now. So now we want to know what charge is on here. So when it's like this, it's going to get charged up to a certain charge. Then when it's moved over here, it's going to share that same charge with the capacitor C2. So what we'll need to start by doing is working out, well, how much charge does it have here? So to do that, we can use our equation for a capacitor, C is equal to Q over V, which tells us that Q is equal to C on V. So we've got 4 times 10 to the minus 6, that's our 4 microfarads divided by 12 volts, which gives us, this is equal to 4.8 times 10 to the minus 5 coulombs. So now that charge is on here, is now distributed between these two plates. So here we've got Q1, here we've got Q2, but those sum together to give us this because charge can't be created or destroyed. So now we've got Q total is equal to Q1 plus Q2 is equal to 4.8 times 10 to the minus 5. So that's one equation that we've got. We also know that because C1 and C2 are connected in parallel like this, they must have the same voltage drop across them. So going back to our capacitor equation, we can write, well, the voltage is equal to Q over C. So we can say that's Q1 on C1, and that has to be the same as Q2 on C2, as they must have the same voltage. So what we're trying to find is Q1. So let's put Q2 in terms of Q1. We can say, well, Q2 is equal to C2 on C1 Q1, because then what we can do is we can substitute from here back into here to try and find our Q1. So we've got Q1 plus C2 on C1 Q1 is equal to 4.8 times 10 to the minus 5. Which tells us, that's a Q1 too, sorry. So Q1 outside of 1 plus C2 on C1 is equal to 4.8 times 10 to the minus 5. So Q1 is equal to 4.8 times 10 to the minus 5. Now we're going to divide by 1 plus C2 on C1. C2, we're told in the question, is 6 microfarads. So we've got plus 6 on 4. We don't need to include the microfarads because it's a ratio here. And so then solving that, we end up with 1.9 times 10 to the minus 5 coulombs. Now the question specifically said, what charge is stored on each plate of C1 now? So when we found this, what we mean by this is that this plate has got, say, plus 1.9 times 10 to the minus 5, and this one's got minus 1.9 times 10 to the 5. So we should say one plate has plus 1.9 times 10 to the minus 5 coulombs on it, while the other has minus 1.9 times 10 to the minus 5 coulombs on it. Okay, so how would we go about marking it? Well, for recognizing that you'll need to make use of this equation, that is 1 mark. For solving this to get 4.8 times 10 to the minus 5 coulombs, that is another 2 marks. And then for recognizing this thing here, this is another 2 points. And for recognizing this as well, that is another 2 points. And then we've got solving these simultaneously, so substituting them in like that is another 2 points. and then solving it to get 1.9 times 10 minus 5, that's 2 points, and then for a statement about what this means for each of the plates is another point. So in total, we've got 2, 4, 6, 8, 10, 11, 12 marks. So this question is out of 12 marks. Okay, so question 2. Okay, so in the first part of this question, we're asked to derive an expression for the magnetic field inside a solenoid. So let's sketch our solenoid like this. And to find out the magnetic field inside it, we're going to need to make use of Gauss's law. So to use Gauss's law, we need to choose a Gaussian surface. So let's take a rectangle like this, and we'll let it have a length L. And Gauss's law tells us that the integral of B dot ds is equal to mu naught I enclosed. So what we'll do is we'll consider what's going along each of these sides of the rectangle. Now, if we assume that this side is a very long way away, then we have no magnetic field at that point. So we can assume that along this side here, the integral of B ds is equal to 0. Now, with these two sides, they will also contribute 0 when we combine them together. One way to consider that is to consider the direction of the magnetic field. If we know it's this way along the solenoid, then ds and B are perpendicular to each other, so that's a 0 contribution. The other way to argue it is that because this one here is going down and this ds is going up, they're in opposite directions, so they will cancel out. Probably the first way to argue it is slightly preferable. So all we need to worry about is this side here. This is the only one which is going to contribute to this. So we've got B times this side, the integral of ds over this side is just the length of that side, so that's L, is equal to mu naught times I enclosed. So what we now need to do is work out, well, how much I is enclosed. So now what we need to work out is, well, how many turns of wire are inside here. So one way to do that is to take the linear density of the turns of wire, so that's N over L. This gives us the total number of turns per meter, and then times it by L. That will tell us how many turns are inside this box, but what we want to know is how much current, and each of these contributes a current I. So what we can say is, well, BL is equal to mu naught times N on L times little l I. Rearranging, well, the L's will cancel off, which tells us that the magnetic field inside is given by mu naught Ni on L. Oh, sorry, that's a capital L, the total length of the solenoid. Now in part 2, we're told that the current varies as a function of time. So we've got I is equal to I naught cos omega t. And we're asked to derive an expression for the induced EMF across the solenoid. So we know that the induced EMF is given by minus n d phi b dt, where phi b is the magnetic flux, so that's b dA. So for our solenoid here, the cross-sectional area, it's just a circle. So we know what the magnetic field is. It's constant inside our solenoid. This has got a constant B inside it. So we've got our B, which is mu naught Ni on L, times our area, which is pi r squared, because it's the area of a circle. So in order to work out the EMF, we have minus n times, we just need to worry which of these change with time. Everything's remaining constant apart from the current. So we can pull out all the constants. So mu naught n on L pi r squared, and then we've got di, and we'll put I naught cos omega t dt there. And so this is equal to minus n squared mu naught on L pi r squared times omega. Now, when we take the derivative of cos, we end up with minus sine. So that negative will cancel out and we'll end up with a sine omega t. So that there is our expression for the EMF. Okay, so in part 3 of this question, we've now got another coil which is placed around the outside of that first one. So we've got this outer coil with a radius r dash, and just inside it is this inner coil like we had up here, this one exactly, with radius r. And what we're asked is to derive an expression through this outer coil. So this outer coil is going to have an induced current in it. So that induced current will come about because of the EMF. So the EMF is given by the induced current, which we'll call I dash times R dash. So this is induced current. This is the resistance of the outer coil. So this is just Ohm's law for the outer solenoid. And then we also know that the EMF is given by minus n dash, the number of turns in the outer coil, times d phi b dt. Now the magnetic flux through here, in this outer region here, there are no magnetic field lines cutting through it because R dash and R are very close. So there's very little area in here. I haven't drawn it to scale. So because there's very little area in there, there's no magnetic field lines cutting through there. So the place where we do have magnetic field lines cutting through is in here. And we know the magnetic field strength in here, it was calculated up here. And so because it's just the same area through which the magnetic field is actually passing, the magnetic flux in this case is exactly the same as in this case up here. So where we calculated d phi b dt up here, we can just use the same value here. So when we do that, here we've got n times d phi b dt, or minus n times d phi b dt. So this is minus n dash times minus n mu naught pi r squared omega sine omega t on L. So this is equal to n dash mu naught pi r squared omega sine omega t on L, and then we've been asked to calculate the induced EMF. So our induced EMF, we need to divide by R dash, the resistance in the outer solenoid. So let's look at how this is marked. There's 1 mark for realizing that we need to use Ampere's law, 2 marks for showing the Amperian loop, 1 mark for somehow recognizing that around this one, and this one, the contribution to Ampere's law is 0. We get 1 mark for showing that the integral of ds is L, so we're just considering this side here. We get 1 mark for calculating the enclosed current, and then 1 mark for substituting in. We don't get any marks for this final expression because that's on your formula sheet. So the first part's out of 7 marks. And then with the second part, we get 1 mark for Faraday's law here. We get 2 marks for calculating the magnetic flux. We get 2 marks for substituting in the magnetic flux, and then 1 point for our final expression. Then with the last part, we get 1 point for this part here, equating Ohm's law with Faraday's law. We get 2 points for substituting in the magnetic flux here, and then 2 points for our final expression. So this question is out of 5 plus 6 plus 7, which is out of a total of 18 marks.